All right, welcome back to our third podcast of the week in the world of the review week of Chemistry 20. We're moving on to formation and decomposition reactions, which are both absolutely review from your from your Science 10 stuff. And hopefully they'll be familiar to you. Inevitably, I see a few common errors that come in, so I'm hoping that we can really nip those right away and make sure that you are on track. So, formation reactions in their most simplest form are taking individual elements and combining them into single compound. And that's the only type of formation reaction that we're going to focus on. But notice, even though I say we're taking singular elements, we still have to take into account those diatomic elements, or the ones that form even wonkier structures like sulfur S8 and phosphorus P4. And as per usual, this just needs to be a foregone conclusion now. Every chemical reaction that you ever write down has to be balanced and has to have correct states of matter. And you can see from the molecular structures of the hydrogen and the oxygen forming the water that we do indeed follow the conservation of matter here. We've got 4 hydrogen atoms in total reacting, 4 hydrogen atoms in total being produced, 2 oxygen atoms in total reacting, and between the 2 waters, 2 produced. So this balancing stuff is logical, guys. That's one of the best things about it. With a formation reaction, ultimately, we are taking potentially 2 or definitely even more reactants. And key thing here is you are making one singular compound, guys, right? So ultimately, remember, individual elements are coming together to form a single product, right? That's key. One product is formed, and these are not individual ions. Keep that in mind. This is not anything to do with what dissociation looked like or opposite, but these are single elements, right? All right. Also, just to make note of, because we're going to get into decomposition in a moment, formation reactions are the opposite of decomposition. And sometimes when things are opposite, it makes it easier to memorize them, because you can memorize one and just remember the other one. Oh, just the opposite, and then we're good to go. So when we're forming different compounds, there's quite a variety that we can form. In this case, we're forming a molecular compound, ammonia. And I wouldn't expect you to know straight out that ammonia is a gas. That's something I'd have to tell you. But just be aware that a variety of different compounds can be formed. Molecular, definitely. However, sometimes, I didn't put it in here. Oh yeah, here it is. That's what I wanted. If we end up with an ionic compound being formed instead, it will always be a solid. This is really important, guys. Like, memorize, know it, be aware. Again, that's specific to if an ionic compound is formed. You are always forming the solid form. If, vice versa, that molecular compound is formed, like ammonia, the state of matter will vary depending on it, right? Like if you form water, it's a liquid. If you form carbon dioxide, it's a gas. If you form an ionic compound, though, always solid. Okay, let's do an example here. When you're doing these, key thing with predicting reactions based upon the type of reaction is catching exactly that. Read carefully, know which type you're looking for. Recognize it's always going to have to be balanced, and then look at what you're forming. Now, the way I usually do these is I don't actually start by writing the reactants. I start with what I form. So I'll write the arrow and be like, okay, I am forming, in this case, sodium chloride. So I'll write the sodium chloride over here. Now, always think back. Don't lose sight of properly doing these formulas. Sodium is a positive cation. Chloride is a negative anion, so the balancing of them is 1-to-1. In addition, this is an ionic compound, which means it is solid. Now, the reactants then are going to be not individual ions, but the individual atoms, right? This is a reaction, guys. They're changing from being sodium metal, shiny, highly reactive, okay, and chlorine gas, greenish yellow, nasty toxic gas, and completely changing into sodium chloride, a sodium ion and a chloride ion. This is table salt, guys. We're taking a shiny metal and a gaseous poisonous substance and turning it into salt, right? Reaction. You start with one thing, you end up with something different. Now, don't forget with chlorine, it is diatomic, so you need to have the 2 there, absolutely essential. And now when we're figuring out the balancing, if I have 2 chlorines going in, I need 2 going out, which means I'm going to need to put a 2 over here. Like I mentioned earlier, notice these are individual elements. This is how formation works, okay? Do not lose sight of that. And this is one single product that's being formed. This is what is characteristic of a formation reaction. It's how you identify it, or given the reactants or products, you can actually get a predicted product. Okay, let's do another example. This next one, instruction-wise, needs to be balanced. There's a hint here. It says the formation. What are we forming? We're forming iron 3 oxide. So iron 3 means we're dealing with an Fe3 plus ion. And oxide, of course, is O2 negative. We can certainly do drop and swap here. I always do the product with formation reactions first. Fe, it'll be the 2 because the oxygen's 2 drops down. O3 from the Fe3 plus. And no exception, formation reactions, ionic compounds are solid when they're formed. What forms them? Split it up into individual ions. Okay, so we are going to have the individual atoms. Individual atom of iron plus individual atom of oxygen. This will be gaseous, of course. Now, from here, we're going to have to balance this thing. We have that similar problem to we had with balancing, where we've got an even number of oxygens on one side and an odd number on the other. That's not going to work. It has to match. So how are we going to do that? We're going to put a 2 here to make an even number being produced. We're up to 6. I multiply this side by 3. Now I have 6 oxygens on both sides. Finish with the iron. 2 times 2 is 4. So put a 4 right here. Dun, 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 dun. Formation is officially done. Now, if this is formation reaction, what if we do the exact opposite? Now, make note, decomposition is indeed opposite of formation. So if formation reactions took individual elements and formed a single product, this time we're taking a single reactant and decomposing it into individual elements. Total opposite, guys, right? So don't get mixed up. This shows the decomposition of ammonia. When it breaks down, you're going to get N2 gas. It's a diatomic molecule. You're going to get hydrogen gas, diatomic molecule. The conservation of matter always has to play out. So the number of atoms going in has to be identical to the number of atoms going out. Now, quite often, people get confused in their brains about decomposition. Please take note, this is in no way, shape, or form. It is not dissociation. Dissociation is showing how an ionic compound dissolves in water, guys, right? It is a process that is fully reversible. If I take, for example, sodium chloride salt and dissolve it in water, if I evaporate the water, I'm back to just salt again. These are reactions. You are ending with a product that is not easily put back to the reactants again, okay? Decomposition reaction, not dissociation. Now, as I mentioned before, you are taking a singular compound and it is breaking down into the individual elements. We do what's called simple decomposition. So it'll always follow that it's breaking down into elements. Okay? So keep that in mind. One reactant is key. And separate elements is key. You can see the decomposition of water is being shown there. We take that molecular compound, which means you got to follow the state of matter it would be. Water's liquid. Yep, start as a liquid, splits up into hydrogen and oxygen. Now, similar though to a formation reaction, if you are dealing with an ionic compound that is decomposing, it will always be solid, okay? Do not lose sight of that. Molecular compounds like water, it'll depend upon the compound. So In addition to that, please don't forget about the states of matter of the metals. You have to look at your periodic table, right? Mostly solid, except for mercury. You have to think about the states of matter of those non-metals. For example, hydrogen, we check out the periodic table. Oh, look, it's a gas, okay? No guesswork, just figure it out. Now let's do an example once again. You're going to have to pay a lot of attention to the problems now because all these reactions are going to be mixed up. So always making them balanced, no exception, and then watch, read carefully. This is a decomposition. Ding, ding, ding. What is it of? Oh, something weird. Sodium azide. And everybody goes, I don't know what that is. Well, yeah, I know you don't know. That's why I give it to you. Okay, the other thing I'll tell you is this is solid, which you wouldn't know otherwise. I wouldn't expect you to. Okay, it is decomposing. So we are not going to write it as though it's producing that. It is going to start as that sodium azide solid. And then it's going to split up into its individual elements, guys, not ions. This is not dissociation. So it is sodium metal, not sodium Na+. Solid metal plus, and it is going to split up into nitrogen gas, not N3 negative, right? N2 gas. Balancing, of course, is always essential. We have that similar problem. I've got an odd number of nitrogens, an even number of nitrogens. Not going to cut it. Let's get reacting to be even. So now I'm up to 6 nitrogens. I can put a 3 produced. Now I've got 6 nitrogen produced. I messed with the sodiums, 2 going in, 2 going out. Dun, 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 it's finished. But recognize that a single compound breaking down into individual elements. This is key. Check out the next example. Balanced equation. Type of reaction is decomposition of what? Nitrogen triiodide. Notice, guys, we've got a prefix, tri. That means this is a molecular compound, which again means I would tell you the state of matter. I wouldn't expect you to know. It is a solid. So we're going to take nitrogen, and it says it is nitrogen triiodide, which means we're going to have Ni3, and it's Ni3 solid. When this thing splits up, it's going to be N2 gas, and iodide is also diatomic. So I2, check your states of matter on the periodic table. Iodine's a solid. Okay, balancing time. We have that good old odd number on one side, even number on the other. Not going to work. Get it to be even so it works. Times this by 2, we're up to 6 iodides, which makes this a 3. Now we just need to mess with nitrogen, and oh look, it already works out. We're good to go, guys. We've got 2 nitrogens being reacted, 2 nitrogens being produced, all is well. Okay, third example. This one gets a little more interesting. This is still a balanced equation, still decomposition, but notice we have a polyatomic ion in here, sodium sulfate. So I wanted to do a little bit more complicated one just to make sure that you can follow how to do this. Now, this is an ionic compound. Sodium is a metal Na+, cation. Sulfate is your anion. So drop and swap, no big deal. We're going to end up with Na2SO4. Remember what I said, it's an ionic compound. It will always be a solid at room temperature. You need to figure that out, okay? The question won't tell you that. This is going to split up. It does not split into sodium and sulfate, guys. The definition of a decomposition reaction is it splits up into its individual elements. That means sodium solid plus sulfur solid. But remember, sulfur's weird, S8. Plus oxygen, not too close, plus oxygen, O2, it's diatomic gas. There we go. Now the balancing, need to be careful, right? Our biggest number is the 8 on sulfur. So let's go with that. Let's try putting 8 sulfurs reacting, 8 being produced. Now this ended up, then we got 16 sodiums, 8 times 2 reacting. So 16 sodiums produced. Oxygen's even higher. 4 times 8 is 32. Okay, well, I have to account for this too. So I'm not going to multiply by 32. I'm going to multiply by half that, 16. 16 times 2 is 32. This is now officially balanced. But notice, individual elements. It is not split into sodium and sulfate. That would be completely wrong. you will be marked wrong. In terms of some questions for you to practice, check out number 5, all. They are all focused on formation or decomposition reactions. Make sure in the assignment you are balancing properly and putting correct states of matter. Good luck. Make sure if you got questions, contact me, ask me. It's no problem.